Hello everyone, and welcome to my first attempt at a flipped classroom. The unit that we're going to be flipping is the measurement unit. It can be broken down into 4 separate categories. The first category is polygons and angles. Then we're going to be looking at perimeter and area of 2-dimensional figures, the surface area and volume of 3-dimensional figures, and then finally we will end with the optimization of both 2-dimensional and 3-dimensional figures. So let's get started with polygons and angles. The first polygon we're going to look at is the triangle. There are 2 ways to classify a triangle. You can classify them with respect to the side lengths, or you can classify it with respect to the angles of the triangle. So the first classification is based on its side lengths. Triangle A, B, and C are shown with the side lengths indicated by those ticks. The first triangle is the scalene triangle, which is called as such because the side lengths are all different. You can see by the ticks on the side lengths of the triangle that each tick is different from each other, meaning that each side is a different length. In addition, since all the lengths are different, then the angles will also be different. Triangle B is an isosceles triangle because the 2 side lengths are equal. There are also 2 equal angles in the isosceles triangle. In the isosceles triangle, you can see at the base of each of the 2 sides that are the same, those angles will also be the same. Triangle C is an equilateral triangle because all 3 sides are equal. You can see this indicated by the ticks on each of the sides that they are of the same length. Consequently, because of this, the angles are also going to be the same. To classify a triangle based on its angles is to either classify it as acute, a right angle, or an obtuse triangle. Triangle A is an acute triangle, which means that all 3 angles of the triangle will measure less than 90 degrees. Triangle B is a right angle triangle because one of the angles has a right angle, which measures 90 degrees. It's important to note at this point that you cannot assume that a triangle has, or a triangle or any polygon for that matter, has a 90-degree angle just because it looks that way. You need to have the square noting the right angle if you're going to assume that you have a 90-degree angle. The only exception for this would be if you're dealing with a word problem that mentions somebody standing on the ground, or a building next to the ground, or a cliff next to the ground. Anything like that, you can actually assume that that person, the building, or the tree will be making a 90-degree angle without having the symbol indicating that you actually have a 90-degree angle. The next triangle property, the third triangle property above classifying each triangle, is the sum of the interior angles of a triangle. The sum of the interior angles of a triangle will always be 180 degrees. So in the triangle that you see on your screen, you have angle A, B, and C. Angle B is 109 degrees. Angle C is 39 degrees. So the fact that we know that the inside angles of the triangle will actually equal 180 degrees, we can figure out the angle A by taking 109 and taking 39 degrees and subtracting them from 180. So as you can see here, we have angle A, angle B, and angle C equaling 180 degrees when we add them up. Once I subtract 109 degrees and 39 degrees from 180, we're left with 32 degrees, which is the measure of angle A. The next property that we're going to be looking at has to do with the exterior angles of a triangle. So the exterior angles of any polygon, not just a triangle, are the angles on the outside of the vertices. So as you can see here, we have this triangle. Okay, and at each point, I've extended the line beyond where it goes. So the angles on the outside are the exterior angles. So for instance, this angle here, and this angle here, and this angle here all represent the exterior angle of a triangle. Sorry about that. So as I was saying, the exterior angles are as such. This angle here is 146 degrees. This exterior angle is 72 degrees. and this exterior angle is 142 degrees. When we add up the exterior angles of a triangle, they will add up to 360 degrees. This is actually true of any polygon, not just triangles. Whether you have a quadrilateral, an octagon, or any polygon with any number of sides, the exterior angles will all sum to 360 degrees, which makes sense if you think about it. I have this diagram here showing, if you consider these 3 points the points on the triangle, and if you move them all in to one singular point, the exterior becomes a circle, which is 360 degrees. Okay, so, and this will be true of any polygon. So it doesn't matter if I have 3 points or if I have 5 points. The exterior angles of a triangle will always sum to 360 degrees. Next, we move on to quadrilaterals. Quadrilaterals are four-sided polygons. There are 5 different classifications of quadrilaterals that we're going to look at. The first, we have this shape here, which has 2 opposite sides that are equal in length. So this side and this side are equal in length, and then this side and this side are also equal in length. In addition, adjacent sides, the sides that are next to each other, are meeting at 90 degrees. So all 4 angles are 90 degrees. Okay, this quadrilateral is called a rectangle. So 2 opposite sides being the same, and the angles are 90 degrees. So again, just like with triangles, when we're classifying them based on lengths and angles. Before I get to B, C, and D, I want to talk about E, because E is a type of rectangle. So E is a square, which has, again, 90-degree angles, and opposite sides are equal, but in addition to opposite sides being equal, every single side is also equal, and that is what we call a square. So a square is a type of rectangle. Quadrilateral B is a trapezoid. A trapezoid has the characteristic that a pair of opposite sides, one pair, will be parallel. So you can see that they're parallel by the arrows here. The other 2 sides don't need to be equal in length. They don't need to be going at the same direction. You could have EH going out this way. As long as you have that one stipulation where one pair of opposite sides are parallel, you will have a trapezoid. Quadrilateral C and D are parallelograms. D is a parallelogram. You have opposite sides being equal, so similar to the rectangle. So NO and QP are equal, as well as NQ and OP. And then you also have parallel sides. So NO and QP are parallel, as well as NQ and OP are parallel. Quadrilateral C is a type of parallelogram called a rhombus. Just as the square is a type of rectangle, the rhombus is a type of parallelogram. And the rhombus has the classification that you have opposite sides being parallel, but you also have every single side being equal in length. Okay, and there's a description of the different types. A quadrilateral has certain properties as well with respect to its interior angles. So as you can see on your screen here, I've drawn a quadrilateral. Okay, in this case it's actually a trapezoid because we have these 2 top lines being parallel, but that's not really the point. What I want to look at is the interior angles of this quadrilateral. What I've done is I've drawn a diagonal from this point here to this point here to indicate that I have 2 triangles. So if I have 2 triangles and I know that the sum of the interior angles of a triangle is 180 degrees, that means that I have the interior angles of a quadrilateral being 360 degrees. Classifying all polygons, polygon is defined as being a closed figure by 3 or more lines. So the smallest polygon, or the first polygon if you want to say it, is the triangle. Then you move to the quadrilateral. 5-sided polygon would be a pentagon. Then you have a hexagon. 7-sided would be a heptagon. 8-sided would be an octagon. Beyond 8, 9, 10, 11, 12, or however many sided shapes you have, we usually denote them as just polygons. So whether it's a 9-sided shape or a 32-sided shape, you're still going to call that a polygon. A regular polygon is a special type of polygon where every single side is exactly the same in length, and as a result, the angles also will be the same. So below here, we see a regular pentagon. So this side is the same as this side, it's the same as this side, which is the same as this side, which is the same as this side, and all angles are the same. So this is a regular polygon. Polygons that aren't regular are usually called irregular polygons. However, we just say polygon, we don't usually say irregular, and only define them as being regular. So, taking a look at these 4 polygons, I wanted to look at the triangle, the quadrilateral, the pentagon, and the hexagon. So if you've noticed, similar to what I did with the quadrilateral, for the pentagon and hexagon, I divided these polygons into triangles to figure out what the interior angles would sum to. So as we saw before, the triangle sums to 180 degrees. The quadrilateral has 2 triangles, so it's 360. The pentagon, when you break it up, gives you 3 triangles, which gives you 540 degrees. The hexagon separates into 4 triangles, each being 180, which gives you 720 degrees as the sum of the interior angles. This process will work for any type of polygon. You can draw all of the diagonals, and you end up getting, multiplying by 180 will give you the interior angles of interior angles of that polygon. There is, however, an algebraic method for us to figure out what the sum of the interior angles of any polygon would be. So when you think about it, a triangle has 3 sides, and you're given 1 triangle. Quadrilateral, you have 4 sides, and you're given 2 triangles. Pentagon, 5 sides, 3 triangles, and hexagon, 6 sides, 4 triangles. So each time you're multiplying 180 degrees, or how many triangles you have, by the number of sides minus 2. So 4 is the number of sides. If I subtract 2 from that, I get 2 triangles, which is 360 degrees. For a pentagon, I have 5 sides. If I subtract 2, I get 3 triangles, which gives me 540. 6 minus 2 is 4, times 180 is 720. So this is true for all polygons. So the sum of the interior angles of any polygon is going to equal 180 degrees times n minus 2, where n is the number of sides you have. So n is however many sides you have, you subtract 2 from that, and that'll give you how many triangles you're going to get, which then you multiply by 180. Moving on from polygons to angles, we wanted to look at the first 3 angle properties, and some of the first 3 being the 3 most important angle properties and that you're going to use the most often, being supplementary angles, complementary angles, and opposite angles. Starting off with supplementary angles, we have a straight line, and in this case I want to highlight the straight line being this one here that I've just traced over. This line here that I'm tracing over now is crossing that straight line. This line is sometimes denoted as the transversal line, or called the transversal line. It doesn't necessarily have to cross through it. It could actually stop at the straight line, but basically it's a straight line that's cutting up this flat line here. Supplementary angles will add up to 180 degrees, meaning the angle on this side of the transversal, which is angle A, plus the angle C that's on the other side of the transversal will add up to 180 degrees. Complementary angles are similar to supplementary angles, except you're dealing with a 90-degree angle instead of 180. So as you can see, I have a 90-degree angle denoted by the right angled square that's at the corner there. Angle X and angle Y are being broken up by this blue transversal, so angle X and angle Y are going to add up to 90 degrees. The third angle property that I want to look at is opposite angles. So when you have two straight lines crossing each other, the angles that are opposite the cross from each other will be equal. So angle A and angle B will be equal to each other. The next three angle properties have to do with parallel lines. They're usually associated with letters, the Z, the F, and the C. So the first pattern is the alternate angles, and that would be your Z pattern here. So as you can see, we have a set of parallel lines with a transversal cutting through them. The Z shape, in this case on your screen you see a backward Z, it also works for the forward Z. The angle A and the angle B are said to be alternate angles, and they are equal. So they're the same measure. The F pattern shows us corresponding angles. Corresponding angles are also equal. Corresponding angle A and angle B are found below the branches of the F. The F could also be upside down, it could be on its side. It still works out that those angles are going to be equal. So that means that the angle on this side of the A and the angle on this side of the B would also be equal because they're above the branches of the F. Lastly, we have co-interior angles. Co-interior angles are associated with the C pattern, as you can see here. Angle A and angle B, although we're dealing with parallel lines and I'm saying they're all similar, alternate angles are equal, corresponding angles are equal, but please do not confuse co-interior angles as being equal. Co-interior angles are not equal, they actually sum to 180 degrees. Okay, so they're different from alternate and corresponding in that respect. Lastly, I'd like to just go over a few examples. The examples that you see on your screen, you can see that the answers are there, and I just wanted to have a quick discussion about why they are the measure that they are. So for instance, the question number 3 that we're going to start, it asks you to find the measure of angle PRQ. It's important to note at this point what angle that actually is that they're indicating. It's pretty simple in this example because you're given 2 of the angles, so obviously you're asked to find the remaining one, which is this one here. But when you're given information like this, when you're asked to find an angle with these 3 letters, the angle that they're actually asking you to show is the one that comes from that middle letter, so R. So angle PRQ starts here, PRQ, and so it's that angle that's right in there. Angle PRQ is 55 degrees based on the fact that we know that the sum of the interior angles of a triangle is 180. So if angle P is 35 and angle Q is 90, I can subtract those from 180 and I get 55 degrees. For example number 4, we're asked to find some missing angles. So for 4A, angle X and angle Z. Angle X can be found to be 70 degrees because the interior angles of a triangle have to equal 180 degrees. Once I found that to be 70 degrees, I can then use supplementary angles to figure out the angle Z is 110 degrees. For B, we have a right angle right here denoted by this square. So over here is 25 degrees, which means that K is then going to be the complement of that, which is 35 degrees. Number 6, 7, and 8 are dealing with our parallel line angle theorems. Angle A is 124 degrees because of corresponding angles. Corresponding angles would be our F pattern. You can see I'm outlining the F right now, and below each branch of that F, those angles are equal. For number 7, angle B is 36 degrees based on alternate angles. You can see the Z pattern. And number 8, angle A is 82 degrees based on the fact that you have co-interior angles. So angle A and 98 degrees need to sum up to 180 degrees. So in order to find that 82 degree, I just subtracted 98 from 180. Next we have some supplementary angles. So we have 120 degrees on one side of the angle, and then on the other side that needs to end up being 60 degrees if that entire line is going to equal 180 degrees, right? This whole line is 180 degrees. So if this is 120, then on this side of the transversal you have 60 degrees. If you're splitting that into two, then each M is going to be 30 degrees. 5, we're dealing with opposite angles. So angle E is going to be 62 degrees because of opposite angles. Then once you know that this is 62, on the other side of this angle is a supplementary angle of 118, since this straight line has to equal 180 degrees. Once I know that this is 118, then I know that F is also 118 because of opposite angles. For 5B, we can do the same process. So angle Y is 147 degrees because of opposite angles. Angle B can be found to be 53 degrees since we have supplementary angles. Then once I know that that's 53, I can use opposite angles to find that this is also 53. However, if you wanted to use supplementary angles, you could do the same thing. You still end up getting X to be 53. Sorry. 33. My bad. 33, 33, and 147. Next, we have these. So when you're given a situation like this with these parallel lines and you're given angles to find, they're usually in alphabetical order. That's the order that they want you to figure out the answer to the measures. So in 9A, I'm asked to find angle A, B, and C, and that's the route that I'm going to take. However, it's not necessarily the route that you have to take. It's just a suggestion for you. So angle A is 75 degrees because of opposite angles. Angle B is 75 degrees because of corresponding angles. And angle C is 75 degrees because of opposite or alternate angles. For B, angle A is 40 degrees because of corresponding angles. Angle B is 40 degrees because of opposite angles. And angle C is 140 degrees because of either supplementary angles, or you could also use the reason of co-interior angles. Okay, that concludes our first look at our measurement unit, which is polygons and angles. And stay tuned for your homework.